Okay, class, I'm going to make a video about the chi-square goodness of fit distribution. And basically, this is a pretty simple, nice test for categorical data. And this test statistic looks like this. It is going to be observed scores that we have. I'll get a better pen than this. There we go. Observed scores, things that we observe in nature, minus what is expected, and then we square that, and then we're going to divide it over an expected value, the same thing as this. And that is our chi-square goodness of fit test. The distribution will look like this. It'll look very similar to the F distribution, where it is going to be positively skewed, and everything will be positive, no negative scores. We will need one more calculation before we can start doing this, and this is called degrees of freedom. You are no stranger to this. And how we determine our degrees of freedom is going to be by rows and columns. So we're going to have rows, and we're going to have columns, and we're going to have expected and observed scores in each one of those cells. And I'll give you an example of that here in just a few minutes after we determine degrees of freedom. So our degrees of freedom are going to be based on rows, how many rows, number of rows, minus 1, multiplied by number of columns, minus 1. So we will come up with a nice little example of what we're going to do with, and I'll share with you the chi-square table. It looks very similar to like a F distribution table. And there's a couple ways of doing this. I've always done it a certain way, and there's an easier way though, however. And it doesn't matter to me how you do it, as long as you are able to do it. I'm trying to close my documents I have up here. I'm trying to find the chi-square table. There it is. So, and I'll share this table with you, like I say. So we're still going to be, this is a hypothesis test, so we're still going to be dealing with the old alpha level, and we're going to use an alpha level of 0.05. I watch a show called Oak Island, and they're searching for this ancient like Knights Templar treasure. And what they do is they find artifacts, and they actually know where these artifacts, where their point of origin comes from. They found a really cool, like 14th, or I think it was 14th or 15th century lead cross, and they sent it in for an analysis to determine how old it was. Well, they were able to do that based on carbon dating, and they were also able to find out where it came from based on a test similar to, well, it's probably a chi-square test, because it's a goodness of fit test. And what they do is they look at all the elements that come from a certain part of the world, and they will match it to that. Does it match that? Does it fit those elements of iron in France, or does it fit the elements of iron in North America? Well, it didn't fit any of those. It did fit, they had developed in, I think it was France or something like that. So, you know, once you get into your professions, you know, you're going to kind of really know what these, you know, tests will actually do for you, and they will do quite a lot based on what you do for a living. And if you even get into this, you know, type of stuff, if you're working with, you know, as an analyst, more than likely you're going to be dealing with a lot of statistics. So we're still going to be dealing with alpha level of 0.05. That's going to determine a critical value, something here. It's going to be a chi-square. Think of it as the same as a standard deviation from the mean out. That 5% is going to be inside of this critical area, the region of rejection. And remember, if your chi-square is larger than your region of rejection, you will reject the null hypothesis. So let's jump right in and let's do one of these real quick. So I'll have to, unfortunately, I have to erase my artwork here, but we'll put it back up. So I'm going to come up with some just arbitrary data, and the homework, I believe the homework is going to be, I wrote it a couple months ago. I think I did, I had two different things I came up with. One was, yeah, this is what it is. It's aggressive behavior after watching video games. So what we do is we set this up, or I set it up, where I'm going to observe boys and girls after watching or playing violent video games. And I, you know, quantified or defined violence as, you know, stabbing, shooting, hitting, kicking, you know, those characteristics. So the character in the video game that you have control of is doing some violence against other people. So that's how I dealt with this. And so I had a population of people who I observed after they had finished watching this game, and what I want to determine is there a difference between boys and girls who watch violent video games in their behavior? Is their behavior violent? Are they cursing? Are they, you know, knocking over trash cans? You know, are they punching holes in walls? Are they, you know, pushing and shoving or cursing? Those type of behaviors. Again, arbitrary data. This is not real research. It's just a homework assignment. And then another scenario that I put up, and this is probably the one I will use for the example today, is I observed teenage boys and teenage girls after they eat their lunch in a mall. Do they, and this is observational research, do they litter? Or do they, you know, put their trash in their respective, you know, receptacle? So let's do that one, because that one's pretty easy, and it's very similar to the aggressive and non-aggressive behavior for the boys and girls after watching the video games. So let's set this up. So I have, let's do males, and we'll do female. Now you can have more variables, and more variables. You can have more, you know, columns, you can have more rows. And for this example and for your homework, so you just understand this stuff, I want to do it very simple. If you can do a simple example, you can do a more complex example. But it's the same thing. I used to be a coach. So you don't start a kid out shooting three-pointers. You start them out, you know, right under the rim and give them confidence and build that up. So we're going to do the same thing here. I've got males and females, and then I've got another category here. I'm going to put litter and non-litter. So those are my rows, those are my columns. Now, all I need to do is plug data into these columns. Remember, with a chi-square, I'm going to have observed. So my observed values are going to be what I'm actually observing in the mall. Okay, I've identified 20 boys. Right here, there's 20 of them. And I've got some that they didn't put, they just left their trash all over the place. And other boys put their trash, they picked up all their trash and put it in the trash can. So I'm gonna have expected scores as well. So I'm gonna divide, and you don't have to do this, but it just makes it a little easier for me to identify these areas as observed and expected. So this is my observed over here, and this is gonna be my expected over here. So I'm gonna label these things so I'll know what they are. Observed, expected. So when I do my calculations, it's easy. Now, I've identified 24 females who litter and who pick up the trash. Now, I'm going to put the numbers in of the boys who didn't throw their trash away, and I observed 16. And that leaves 4 who put their trash away. Boys tend to be more messy than girls on average, so let's see what happened over here. Well, geez, the litter girls, there weren't very many of them. There were only 6. And so that leaves 18 girls who threw their trash away. Now I have all my data so I can start calculating my expected values. Now there's 2 ways that you can do this. I'll show you the way I always did it, but there might be an easier way of doing it. I'll show you that, whatever works for you. So I'm going to add my first row up, the litterers. I'm gonna add those up. 16 plus 6 is gonna be equal to 22. So I got 22 over here. Now I've got 4 and 18. 4 plus 18 is equal to 22. So that's kind of, I got 22 litterers and 22 non-litterers. I didn't think that was gonna happen. So if I add those 2 things up, 22 and 22, I should get 44. And if I add these 2 things up here, my males and females, I should get 44. So 20 plus 24 is 44. So I'm off to a good start. Now the only thing I have to do is determine what my expected scores are here. And it's pretty simple to do this. So I'm gonna go ahead and get my expected scores in, and then we're gonna determine our degrees of freedom. So let's go ahead and do expected scores real quick. So in order to do this, what I do is, this is gonna be a kind of a weird example because I've got even numbers. So 22 divided by 44 is gonna be 50%. So these numbers are gonna be basically the same, so 50%. And I'm gonna have 50% down here. So what I can do to find my expected score is take 20 multiplied by 0.50 or 0.5. So 20 times 0.5 gives me 10. So 10 would be my expected value. I'm going to do the same thing with this number here. Since it's the same, it's going to be 10. Now I'm going to do the same thing here. So 24 times 0.5 is equal to 12. This is the same number, so it's going to be 12. So those are my expected values. Now, you can do this, probably an easier way. 44, then you do 16 divided by 44, 0.36 Yeah, I mean, we can do this, you know, another way, but this is a pretty easy way to get to this. So let's go ahead and add this up. That looks correct. So degrees of freedom, like I said, is rows minus 1 times columns minus 1. So I've got 2 rows. 2 minus 1 is 1 times, I've got 2 columns. So 2 minus 1 equal to 1. So 1 times 1 is equal to 1. So I've got 1 degree of freedom. So when I look at my table, one degree of freedom at the significance level of 0.05, I've got 3.84 for my critical value. Now, in order to do this, I need to work my formula. So I've got 16 and 10 minus 10 divided by 10 plus 6 minus 12 divided by 12 plus 4 minus 10 divided by 10 plus 18 minus 12 divided by 12. So let's do that. And of course, I've got to square these. I forgot about that. That will get rid of any negative number that I have. It's, you know, very similar to the standard deviation. When we have deviation scores that are negative, when we square them, it turns them into positive numbers. So it's the same concept here. So if I've got 16 minus 10, that gives me 6. So 6 squared is equal to 36, and I'm going to divide that by 10, and that's going to give me 3.6. So 3.6 plus, and then I'll do this one here. So 6 minus 12 is going to be a negative 6, and I'm going to square that, and that's going to give me 36. And I'm going to divide that by 12. That's going to give me 3. 4 minus 10 is going to give me a negative 6. And when I square that, it's going to turn it into a positive. Again, 36 divided by 10 is going to be 3.6. Plus 18 minus 12 gives me a value of 6. Squares 36 divided by 12 is going to give me 3. So when I add all these things up, I got 3.6 plus 3 plus 3.6 plus 3 gives me a grand total of 13 point. Is that right? Doesn't sound right. It might be right. Yeah, that's right. Okay, 3.6 plus 3 plus 3.6 plus 3, yep, 13.2. So my chi-square is equal to 13.2. So if I put that up here, 13.2 is way over here in this, alpha range here, the critical region is 13.6. So I would say that yes, I can reject the null hypothesis, and the null hypothesis would be H naught is that the expected, or my observed values are equal to my expected values. And my alternative hypothesis is going to say that my observed values are not equal to the expected values based on an alpha level of 0.05, which is basically going to be in this 5% region of rejection with 1 degree of freedom. So that's how we can go about doing this particular chi-square goodness of fit test. And what I'll do is, like I say, this is going to be very similar to your homework. I'm going to give you, 2 rows and 2 columns, and it's probably going to be the violent video game thing, and it'll be boys and girls, but you can put this into many, many other type of scenarios, and it's a really good fit for observed data. All right, have a good day, and I'll make another video for you.